In this recording, we're going to try and introduce you to some software I developed over the last couple of years for both processing of giant radio galaxies in a search together with Heinz Sandernack for these objects, plus looking at how to separate out diffuse emission from compact sources in terms of inside clusters of galaxies. And this software will actually do both of these things, so we're going to try and have a look at how to do this. This is a classic giant radio galaxy, 3C236, discovered by me a long time ago. And we're going to try and look at it with some more modern tools than were originally available to us back in God knows when, about for this thing, years and years ago. So one of the things we want to do, amongst other things, is there's actually two quite bright sources here, which are actually background sources. Along the way, we want to actually remove these things from our integrated flux density, and there's also a little guy here, which is also a point source, which we want to remove. Now, the work I'm going to plan to get was partly stimulated by a paper Larry Rudnick wrote back in about 2002, where he was trying to separate out compact from diffuse emission. And a lot of the ideas that we're going to discuss here were created by him. Essentially, he looked at a tool called mathematical morphology. Mathematical morphology allows you to create, once you've created something called a structure function, you can then use your structure function to create what's called something called an opening, which is basically using a structure function to create, first of all, what's called erosion, followed by dilation. And if the source is reasonably smooth, you will actually get the structure function to reasonably well track through your source of interest, where here we have a one-dimensional example of that. But there's still going to be fine features in our diffuse in our original source, which probably aren't going to be removed when we subtract our structure, our opening from the original image. When we subtract our opening from the original image, we're probably going to get something like this, where we have kind of a noisy background, but then we have these two peaks here, which were not replicated in the original image, and they are what, in current mathematical terminology, they're called white top hats. And we can actually then take a white top hat and say, okay, we want to detect the white top hat above a certain noise level, and then we can create a mask of these white top hats, and essentially then we could take the white top hats and then subtract them off the original image, and then we would get actually an original image of purely diffuse emission, and we don't have to use this opening object. Now, how did we end up using this stuff? In actuality, first of all, I should mention the software used here, which you can download from the internet. Something called Shapely, which was developed originally, I think, as a supporting tool for geographic information systems. Shapely has a nice feature called a super polygon, which means you can actually take our thing here and actually take subsections of this and join them together into a super polygon, which then has the parameters of the entire image. Scikit image has all sorts of mathematical functions for actually doing this, creating this thing called an opening and the corresponding filter to what in mathematical morphology we now call a white top hat. And I would strongly suggest that if you want to get way bit more information about what's called a white top hat, more structure functions, etc., there's a really good There's some really good YouTube videos by somebody called Udacity, Udacity, And I suggest you look them up, and they have really good YouTube videos of how structure functions and mathematical morphology actually works. Anyway, we're going to use these particular parameters to investigate things. One thing I should say for people who were using this system in an original variant, I've now changed the, originally I think we had things like filtered, etc., descriptions of files. And they were actually when I came back to look at this thing again, they were very confusing, and I've tried to now use things like 3C236. So we have an opening.fits, when we have a white top hat.fits, and we can have various things. We want to create masks opening, etc., masked original images, and we want to have white top masks, etc. So as much as possible, we've tried to use terminology which equates to top hat functions in the current system. So we're going to let's see. We want to use. So we're going to use this example script, and let's get rid of this guy now. We've seen enough of him. Now we're going to first of all, let's go through and this is a way of describing things is a bit clumsy. I'm going to try and turn all this stuff in eventually into either a JSON file or a Python dictionary, but we're stuck with a few things, always using the name .csv. Originally, we have a 3C236 where we use something called the 3C236.csv file, which we can say here it is. Where this essentially seems that FITS files seem to often contain kind of a very different variations on how they describe the frequency. So I tell myself what the frequency is in gigahertz in the first line of the file. Then we have name 3C236, which is why we're stuck using endless 3C236s. And if we happen to know it, we can actually say we can tell it what the redshift is. This LAS thing is meant for search areas for looking for giant radio galaxies, but we need to know the redshift in order to get anywhere with what they actually are. And if you know the spectral index, you can include that here. I don't really recall what the spectral index was for 3C236, so the system will just say, oh, it's minus 0.75. And so let's go now, and we're going to go through these operations here. And we're going to link the original image, which has a capital FITS. And then we're going to go and get parameters for this particular object, get galaxy parameters. We have a theoretical -th means essentially the noise limit above sigma. So if we find a noise limit of like 0.1 of RMS, then our theoretical cutoff limit for actually doing something useful would be 0.6 of whatever it is, millijanskis or whatever. So we're going to essentially cut off these things. We don't want to go right down to the noise, so we have a cutoff level of 6 times whatever the noise is. Let's go. Don't worry about what -s means at this stage. Copy that. Paste. So now here we have. Let's see this. So here we have our original image, and we can go in and select the things that we want to select for use with our super polygon. So if we left click on this, it sort of marks areas we're interested in, and marks interest here. Now, our mouse offers us with several manipulations here. Let's say first of all I make a mistake, for example, and I include I happen to include one of these background sources in my original image, and so I would click on this thing. And then I say, oops, I didn't mean to include that. Then a right click of the mouse will get rid of all these things. If you actually click on the middle mouse, let's see, go on to this. We're going to have the first two images, and we're going to have then the third thing should be that. So we now have 3 lobes, 1, 2, 3. If we now click on the central mouse button, we'll save an image of this situation exactly as it is now, so you can label the sequence of images that are going to be processed. But we've now created a super polygon, so it's going to report to us all the structure as if this whole one is one giant image. Now the other thing is to note is that Matplotlib, for some weird reason I really don't understand it, will not send information out from the Matplotlib display to the downstream image, which is going to do the data analysis, until you shut the image down with turn Matplotlib image off by using the window closing button. So that's happened, and it's sent out the the individual lobe parameters, where they are, blah blah blah, and then we can look at see what the actual 3C236 parameters are. So we know, first of all, parameters derived from Brisoro as a way of taking little areas of the image and selecting what the noise is in these little binned areas and taking the median of that noise level. And so it turns out, let's see, where's the noise level, blah, 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 blah. Computer, it's here somewhere. Yeah, Brisoro median noise is 0.68 millijanskis in this thing. Okay, so from our super polygon, our computer-generated source angular size is 2455 arc seconds. Then we can use our CosmoCalc, which actually now contain a Hubble constant of 70 kilometers per second, etc. It will tell us the actual apparent projected angular size in kiloparsecs is 4,500 kiloparsecs, or 4.5 megaparsecs. So it's still one of the largest known radial galaxies, about 4th or 5th place, I think. And then we can actually use the fact that we have a super polygon. It'll tell us the integrated flux density, including the nucleus, is about 8.6 Janskis. It contains 0.6 gigahertz luminosity and is scaled 1.4 gigahertz luminosity, since 1.4 gigahertz is kind of a standardized things for preparing luminosity functions, etc. It drops from 0.69 to 2.13 times 114. Then we get individual polygon parameters for each of the lobes as well. And so we have the 2 lobes. You can, as well as to find the point source in the middle, it figures it's out as actually a point source because the peak flux density is less than 20% of what it claims the integrated flux density is, which is so far not really significant. So you can look at all this stuff for various individual operations, etc. So let's go quit. Next thing we want to do is get our morphological images. So we're going to do this particular thing. Again, now here we want to get our morphology images with a slightly higher, let's see here, we did get the morphological parameters. Now we're going to get morphological images, which means we're going to try and use one of those original images minus the opening to actually try and see if we can separate out point sources from diffuse images. So let's copy that. And let's see what we get. Yes, okay, so we actually did a very good job of getting rid of our most of, we have the original source minus the opening, and there's actually a few areas where our residual point sources, and that is the compact features, the original source minus the opening. These things are still peaking above that because, of course, things aren't necessarily totally diffuse in the image. And of course, I just tapped on a non-existent lobe one, so we removed that. So you want to actually add these. These are actually probably still part of the original diffuse image. So you want to add these back into the diffuse image and try and avoid it. And adding in here, we can see we've actually got these point sources here removed. And we've got the point sources out here removed. So let's actually now zoom in and add the stuff we want to add back in. So let's go and zoom things in here. So we want to add this guy as a point source. We want to leave him. So we're going to add this one, this one, this one. Let's zoom in here again. Let me try and be super accurate here. Oh, come on, come on, come on. We're going to zoom out. So we've got all those ones. Going to zoom out again. Going to now zoom in down here. And so we're going to leave these two guys out of adding back because they're not what we want. We want to add in this guy. Let's see, that's a little bit more in actually. So we're going to add in, let's see, I didn't do that quite right. Yeah, let's just do here. Okay, we've got that one, I don't care about that one. And so we've got these three we're going to add back in. 1, 2, maybe I'll try and get that one. Let's see. Now, so we're going to send our, again, shutting our point source things down here. Now what we've done by that, as we'll see here, is let's see. Look at this thing. Now we have our final, we have a comparison of our final, this is actually taken a bit earlier, so we still have, this was a mistake I think I made back when I actually took this picture. But we have essentially have our final diffuse image with all of these point sources are gone. But here is now our final point source image. So if we wanted to actually get values for these double point sources here, we could do so. All this stuff here, which was in the originally part of the nominal point source background, is now being removed. So we got rid of that. So this is essentially a comparison, totally of final and diffuse and compact objects. Now what we want to do is, since we've been integrating this stuff, we want to actually see what our we want to see how much of the smooth emission we can actually see. So let's go and see if we can convolve this stuff. Leave full screen. Now I've got to be careful here because I messed up on this thing before. We want to again get rid of the 3c236.fits. We want to convolve we want to link the final image.fits to again to that. And then we want to convolve the image using, this is a convolution thing that's based on AstroPy image, and it works pretty nicely. Okay, conv image of 3c236 fits. Okay, and we've now convolved that. So let's get galaxy parameters for this character. We're going to down with a smoothed image. We're going to use a theoretical arm as 3 times the noise. And here's what we see. Now, first of all, it's something I'll just point out here. Let's zoom that up. You can see actually, because of various visualizations, there's 3C. It looks like there's actually, when you use this particular visualization scheme, there's some kind of ramp, which in the original apes reduction back in God knows when, 1993 or something like that, was not really noticeable from whatever visualization we had in available to us. But we can see there's a little bit of a ramp going from one side of the source to the other, and so there's probably the fringe. This is with the Westerbork telescope, and at 1 hour angle, the fringes are going to completely add up parallel to this source, and the other ones they're going to be resolved. So somewhere along here, we didn't quite calibrate the shortest baselines properly, I don't think, but it's very low level, so we're not going to worry about it. Anyway, here's our final image, and we're going to just do integration of lobes 1 and 2. And let's see what that is. So our source now here, since we removed 3C236, is only 3,400 millijanskis, and we've essentially lost 5 janskis of emission because we're now no longer using 3C236. Basically, otherwise, though, our convolved source here is because we actually integrated things back closer to the nucleus now with the smoothing. I don't think there's too much difference between our convolved source and the original unconvolved image for this lobe. Yeah, so that's, you can go and compare these things in detail and see how we things improved or changed. Not very much, I don't think. So that's basically all about this. You can actually run this whole script by yourself, and it'll run things in detail. And thanks very much for your time. Hopefully I didn't bore anybody too much.